Hi students, and welcome to the HSC Chemistry and the acidic environment video series. In this one I just want to have a quick focus on neutralization reactions. Now we've previously up to this point looked at different types of acids, bases and salts, and we've actually started to have a bit of analysis at the types of or the nature of different types of salts in terms of their neutrality, acidic or basic nature. But in this particular video, I just want to focus on the actual neutralization reaction itself. Up until this point, pretty much, we've defined neutralization as a reaction between an acid and a base. And in order to demonstrate that reaction, we've used strong acids and strong bases, such as hydrochloric acid or sodium hydroxide, in order to demonstrate a neutralization reaction. In a neutralization reaction, water is always a product, and we also form a salt, which in the case of the example given above would be something like sodium chloride. When we think about the net ionic equation for this particular reaction, so if we write the full equation, we get hydrochloric acid, aqueous solution, plus sodium hydroxide in aqueous solution, produces water as a liquid, and sodium chloride also in solution. So when we separate this into its ions, we have H+, Cl-, Na+, OH-, H2O liquid, which doesn't ionize, so, well, not very much. So we leave it as its liquid form, and sodium and chloride ions. Now, of course, we know that when we have ions that are common on both sides, we can cancel them out, so the sodium and the chlorine are both going to disappear, and it means that our final equation is actually going to be H+ plus OH- gives H2O liquid. If we use a hydronium ion instead of hydrogens, we now know that when the hydrochloric acid is in water, it donates its proton to a water molecule to produce a hydronium ion. So there's a hydronium ion, obviously in solution, combining with an OH- ion, also in solution, and that will give us two water molecules. And what happens in this case is the proton is being donated from the hydronium ion to the hydroxide ion, leaving one water molecule and forming one water molecule. One of the things that we notice when we start to look at different types of neutralization reactions is that we can simplify them down to be proton transfer reactions. So a proton being transferred from one species to another. Often this is the hydrogen from an acid combining with the OH group, the basic part of the base, but it's not the only example of these sorts of neutralization reactions. So effectively, what we've shown is that when a proton is transferred from an acid to the hydroxide ion of the base, we have a neutralization reaction. And one very important thing is that all of these reactions, irrespective of which acid or which base we use, are exothermic. They all release heat. So they release energy in the form of heat. So you can actually monitor temperature changes. When heat and neutralization is measured for a range of different types of acids and bases, as long as they are strong acids and bases, and that's what we're focusing on at the moment, the amount of heat released is always the same. It's very, very close to, anyway, 57 kilojoules per mole of water formed. So what this means is that we can actually write an equation to represent this process. So the specific equation for the delta H value will be either H+ plus OH- going to H2O liquid, or probably more correctly, the hydronium ion combining with a hydroxide ion to form two H2O molecules. Just remember, of course, that the delta H, the negative value, which indicates XO, and 57 kilojoules is per mole of water formed. When we study the heat energy for a range of different strong acid-base reactions, we find consistency in these values. And this suggests that this reaction is the one that's occurring all the time. So the actual nature of the acid and base doesn't matter. The ions that are common from the acid and the base don't matter. So the ones that are forming the salt, the soluble salt, are less important in affecting the net value of the exothermic reaction than the neutralization or the proton transfer itself. So production of salt and water, or what we will now refer to as a transfer of a proton species, a proton transfer from a donor to an acceptor, is a good definition for a neutralization reaction. So in summary, two important points about neutralization. They're just little updates on what we've looked at before. Firstly, that they may be regarded as proton transfer reactions. And secondly, that they are exothermic. And I guess thirdly, that these exothermic reactions have a delta H value of negative 57 kilojoules per mole of water formed. Thanks for watching.